Alright, so this question is about the maximum speed in which a car can round a turn with a radius of 80 meters on a flat road if the coefficient of static friction between the tires and the road is 0.8. So here's my flat road, and so here's my curve, and I've kind of drawn this picture to be like a perspective where if I'm looking at the back of the car, these are the tires, and there's the back of the car, and there's the back window, and the tag and the tail lights, and this is the curve radius, so that's going to be R, and so this car is kind of going around this curve following this path. Again, it has a tangential velocity, and we want to know what is that maximum tangential velocity. What is that maximum speed? I know the mass of the car, I know the radius, and then I know that there's a friction acting on the car. So because this is really a forces question, let's look at the forces acting on the car. So let's draw a free body diagram of all the forces acting on the car. I'm going to just draw a box to represent the car. The car's on the earth, so there's a gravitational force acting on it straight down. It's sitting on the road, so there's a normal force from the road up onto the car. And then what keeps the car from flying out of the circle is that there's a friction force directed towards the center of the circle. So a force of friction. And just to remind myself, I'm going to write that this is the center, so I remember that it's pointing towards the center. So if this is my x-axis, and this is my y-axis, I can think of summing my forces in the x direction as being the force of friction. And that's definitely unbalanced, so that would equal ma. And not just any AC, because it's pointing towards the center. It's a center-seeking force. The friction force is center-seeking, and so the acceleration is center-seeking there. Now if I sum my forces in the y direction, they are a normal force up, a weight force down, and those are balanced. It's not accelerating in this up and down direction here. There's only an acceleration towards the center so that the car can constantly change direction as it goes around this curve. So now let's put these things together. So from over here, the force of friction is equal to ma sub c. Now if you remember, so now let's look at this sum of forces over here. If the normal force is equal to the weight and the friction force is equal to mu times normal, the centripetal acceleration is equal to v squared over r, then I can make some substitutions. That means that my normal force will be equal to the weight, which is the mass of the object times the gravitational field. So then let's stick this in for this force normal up here. So we'll have mu times mg is equal to mv squared over r. Now I can see that I could divide by m on both sides. That's kind of exciting. So I can divide by m on both sides. And so what does that leave me with? That leaves me with mu g is equal to v squared over r. Now I'm looking for the speed. So if I multiply by r on both sides, I'll have r times mu times g is equal to v squared. Don't forget that. Then we'll take the square root of both sides. So that means that v would be the square root of r mu g. Now let's look to see what we were given. We were given that the radius is 80 meters. The coefficient was 0.8. We're going to use the estimated 10 meters per second for the acceleration due to gravity. Then we're going to take the square root of this. So this leaves us with a final velocity of 25.29 meters per second. Now, let's go back and think about what we just solved. We were given that this car is going to negotiate this turn, this 80-meter flat road with a coefficient of static friction. And so we were looking for this maximum speed. What is the maximum speed? So I just drew a little picture here. Drew a free body diagram, summed the forces in the x direction and in the y direction. We made some connections with the forces. And set the normal force was equal to the weight. The friction force was center seeking, so equal to MAC. Made our friction force substitution, our acceleration substitution. Then we were able to substitute the normal force as being the weight in this case. Then the mass canceled out because I had it multiplied on both sides. Then I was able to solve for this velocity as being the square root of r mu g, kind of looks like root rug. And then the last part of the question asks us to identify if the result is independent of the mass. And right here, where we cancel the mass out, tells us the answer to that is this result independent of the mass of the car? Yes, because the mass canceled out. So it's independent of mass.